Hello. We will continue our last lecture where after a short break I will continue the derivative topics with directional derivatives and the higher order derivatives and the Bayesian matrix will be introduced in this part inshallah. Okay, what's the direction derivative? I want you to understand the following, that in multivariable calculus the directional derivative generalizes the idea of a derivative of a function if several variables, but instead of measuring the rate of a change in just the x and y direction, I can measure the rate of a change of the output relative to any other direction. This is why we are using the directional derivative. The basic idea, you will have f of xy, which is a function and let you be a unit vector, which is a vector of length 1, and this is actually, I went through it either to deal with a vector in the general case or to deal directly with vectors as unit vectors. In order to compare, and that's a comment in the slides, more than one case, it is better to use unit vectors. How to bring a unit vector, ya Omar? In order to make a unit vector, all I have to do, as you will see, is to divide the vector component on its magnitude, or the magnitude or the norm of this vector. So once more, let f of xy be a function, let u be a unit vector, which is a vector of length 1, I told you how to break it, representing a direction, the directional derivative of f at a point x or y naught in the direction of u. Measure how fast it changes as we move from x naught, y naught in that direction. The directional derivative is defined by this relation, where, if you remark, it is the limit of h tends to 0. Remark, I want you also to remark at the time being that the derivative in the x direction or the derivative in the y direction, the partial derivatives, they are actually a special case from the directional derivative. But they are directional derivative in the direction of the canonical system. What the canonical system? If I'm in 2 dimension, 1 and 0, and 0 and 1. Okay? If in 3 dimensions, 1, 0, 0, 0, 1, 0, 0 and 1, which is also get you back to the linear algebra. Okay? So, if I want to have directional derivative, the law is really very simple. The derivative of f in the direction of u, so once more, it's the direction of f at u, okay, in the direction of u, at the point x naught and y naught. All I have to do is to grab my function at x naught plus h times y1, and then y naught plus h times u2. What's u1 and u2? They are the components of your vector. That's, you are evaluating the rate of a change in its direction, okay? And it is minus f of x1, y1 divided by h. If you remember, if we do derivative with respect to x, we usually write x naught plus h times y1, which is 1. This is why you saw x naught plus h. And this is going to be y naught plus h times 0. So that's the partial derivative in the direction of x. The partial derivative in the direction of y, exactly the same. It's going to be x naught plus h times 0, y naught plus h times 1. This is why you saw 1 in the direction of y. But in order to generalize it, I will use u1 and u2 as the component of the vector that I'm evaluating the directional derivative in its direction. So it's going to be u1 and u2, which are unit vectors, as you can see. Directional derivative using gradient vector, that's the formula that I'm going to use in order to evaluate the directional derivative. All I have to do is to evaluate the gradient vector, we can do that, dot u, which is the unit vector at the direction that I want to evaluate. Okay, طبعا the gradient vector we already know, partial f, partial x, partial f, partial y, then we will do the multiplication. Mainly the gradient f points in the direction of maximum increase of the function. The directional derivative measures the component of this increase along the direction of u, which leads to in duf greater than 0, the function increases. duf equal to 0, no change in that direction. duf greater than 0, the function decreases. So using directional derivative, I can speculate how the function, the behavior of the function, is it increasing in this direction? Is it decreasing in that direction, or is it a constant, or there is no change in this direction? Okay, important special cases, as I told you, if the u vector is 1 and 0, then you are talking about the partial derivative with respect to x. The directional derivative will be the partial derivative. If I'm using u as 0 and 1, in this case, it will be the partial derivative but with respect to y. If I'm talking in 3 dimension, then also the third will be 0, 0, 1, and in this case will be partial f, partial z, if it applies in 3 dimension. Partial derivative are just directional derivative along the coordinate axes as we saw. So, for example, if I want to evaluate, if I want to evaluate the directional derivative of the function x square y square, okay, خلي بالك بيقول find the direction derivative at the point, يبقى دي point, okay, in the direction of the vector. So if something like this was required, all I have to do, once more Mr. Omar, I will do 3 steps. The first step is to bring the gradient vector. So the first step to grab the gradient vector of f, which is going to be differentiating with respect to x, differentiating with respect to y, which is 2y. That's the gradient vector. The second step is to evaluate the gradient vector at the point. I want you to evaluate the directional derivative at 1 and 1. So all I have to do is to evaluate the directional derivative at 1 and 1. Let's substitute Mr. Omar. يبقى إذا substitute instead of xy by 1 and 1. So it's going to be 2 and 2. So it's a 2 times 1, 2 times 1, so it's going to be 2 and 2. That's the first step. Second step, let's normalize our vector. This is the vector that we are dealing with. Get its norm. How to get the norm of a vector? It's very simple. The norm of v is just the square root of the first component to the power of 2 plus the second component to the power of 2, which is a root over 5. Now I can get my unit vector. So v as a unit vector, it's going to equal to the components of the v vector by the norm of v, which means it's going to be a mercy 1 over root 5 and the 2 over root 5. In order to get the directional derivative, which means d in the direction of 1 over root 5 and the 2 over root 5 for the function at the point 1 and 1, all I have to do is to multiply these two suckers in each other. So it's going to be 2 and 2 times 1 over root 5 and 2 over root 5, as you can see. So it's going to be 2 plus, I believe, 4 over root over 5, which is going to come up to 6 over root 5, as you can see. That's the directional derivative evaluated at certain point in certain direction. Remark, Omar, if I can evaluate the directional derivative, but not using a unit vector. In this case, it's not going to be easy on me to compare between various directions, especially if I'm studying the behavior of certain function in multiple directions. Is it increasing? Is it decreasing? It's going to be different. But in order to make it as clear as possible, use unit vector as you saw. So once more, if I want to go through this problem using the slides or the animation in the slides, it's going to be exactly the same as I told you, and those are the parts that sent to you previously. So first step, I will have normalize the direction vector. So I will have to normalize this guy. It's going to be 1 to the power of 2 plus 2 to the power of 2, which is root 5. So I will divide 1 and 2 over root 5. Already done. Okay, get the gradient vector, which is 2x, 2y. Then substitute instead of x and y by 1 and 1. We already have it. The final step is to multiply them together. So that's the gradient vector times the unit vector, multiplying them together. I will multiply the first component in the first component, plus the second component in the second component. This is why you have 6 over root 5. By the idea, once more, I can evaluate directional derivative of f at a. And I can evaluate using the unit vector. It is favorable in the case of comparisons. Once more, Omar, he is asking you to calculate the directional derivative of f along the vector 1 and 2. Okay? At the point 3 and 0. Similar steps. I will do exactly the same. First of all, I will bring the gradient vector, which means I will differentiate this function. It's just with x, it's just with y. Then I will substitute by the point. Keep it. Then I will normalize this vector. So I will need to divide on the magnitude of this guy. So once more, if I want to do so, this is going to be the first partial derivative with respect to x, with respect to y. That's the gradient vector. Then I will substitute with the coordinates of 3 and 0. So once you do so, it's going to be 0 and 4. That's the substitution of the gradient vector. The second step, I will make a normalization. It's going to be 1 plus 2, so it's 1 over root 5, 2 over root 5. Then I will multiply them together, applying the rule. So 0 and 4 dot the normalized vector, which is going to come up to 8 over root 5, as you can see. I usually prefer to use the unitary shape of my vector, and this is how I will get the value of the directional derivative, but using the unit vector. Another problem, which is the same as the first one, x squared y squared compute the value of the directional derivative of f at the point 2 and 1 in the direction of the vector 1 and 1. Once more, these are the gradient vector 2x, 2 and y. I will get the value of the function at 2 and 1. It's going to be 4 and 2. So just put 2 in here and 1 in here. It's going to be 4 and 2. Get the normalized form of the vector. So I will have to evaluate the norm first. What's the norm, Omar? The norm of this vector, it's going to be the square root of the first component to the power of 2, second component to the power of 2, which is root 2. So all I have to do is to divide these two components on root 2. That's the second step, getting v as a unit vector, as you can see. Now to the final step, multiplying the vector in the direction, I will get 3 root 2, as you can see. I've also inserted for your lecturing, I've added another example, because I know as much examples as it exists, it will make you familiar with the problem, with the steps and everything. So once more, essentially, I will get the gradient vector. Then I will substitute in order to get the values. I will get the normalized form of the vector. Then I will multiply both of them together. Once more, we use normalize the directional. Simply, we use the unit vector in order to make it easy for comparisons, especially between more than one case. I want to talk to you now with the second order partial derivative and the second order directional derivatives, which is exactly the same rules, but instead of dealing with the main function, I will be dealing with its derivative. So it's the same rule, but instead of using the first function or the main function, I will use the derivative, or I will apply the rule using the derivative of this function. Of course, this form is the xi, xj. So I've taken the first derivative, or the first form was xj, and then substituting by xj, as you can see, I have here the canonical vector of ej appearing to us, and exactly the same steps will be on. For example, if f of x2 x cubed into 1, f dash x will be 6x squared. So if I needed the second derivative, all I have to do is to apply my rule on this value, which is, that's the function of f of x cubed. I'm applying the rule, but instead of having f at 1 plus h minus f1, I'm using f dash. So instead of using 2x cubed plus 1, I'm using 6x squared. If I make a substitution by 6, 1 plus h to the power of 2, that's the shape, minus f dash at 1, so replacing is going to be 6. I will simplify the denominator. The denominator is really very simple to simplify. All I have to do is to multiply 6 by 1 plus 2 over h plus h squared minus 6. So this is going to be the limit, as you can see. It's going to be the limit of 6h squared plus 12 over h. Take h as a common, so you will end up having 6h plus 12. Apply 0, so this part will be cancelled, and the result will be 12. And that's the interpretation of what happened, the meaning of the second derivative of this function, as you can see. This rule can be generalized for more functions other than for functions in several variables at this problem. Here I want to get the mixed derivative. This is f of xy, so I have two inputs. The function is x squared y plus ex divided by y, so I will get the derivative with respect to x. Then I will differentiate this one with respect to y. This is y. That's the derivative with respect to y. So getting partial 2f partial x squared, we're really familiar with this. I will differentiate this function once it goes with respect to x, so it's going to be 2y, and this is going to be x to the power of y. If needed to get partial 2f partial y squared, although it is not required here, but I put it with our work in order to more training for you. For partial f, the mixed derivative, I will get the first derivative, then I will differentiate with respect to y. So differentiating with respect to y, it's going to be 2x, and this guy is going to be ex to the power, ex to the power of y, e to the power of x, I'm sorry, divided by y, as you can see. So that's the derivative, the mixed derivative. Now I will come to the Hessian matrix. The Hessian matrix is really very important and also really very simple. It is just a symmetric matrix, okay? In the two dimension, that's the shape of the Hessian matrix. It is the second derivative usually used for more analysis, like getting the extremum points and so on. I will go through this in those couple of slides. And if you remark, for functions, several variable functions running from R2 into R, this is going to be the form f double x, f double y, f of x with respect to y, f y with respect to x. So if I'm dealing with Hessian matrix in 3 dimensions, what do you think the shape is going to be? So if I'm talking about h of f, x, y, and z, the dimension will be 3 by 3. And it's going to be partial 2f, partial x squared, partial 2f, partial y squared, partial 2f, partial z squared. And then this guy will be partial 2f, partial x, partial y, partial 2f, partial x, partial z. And in a similar manner, I will have partial 2f, partial y, partial x, partial 2f, partial y, partial z. Then I will have partial 2f, partial z, partial x, partial 2f, partial z, partial y, as you can see. That's the shape of the Hessian matrix in 3 dimensions. Okay, so in multivariable calculus, the Hessian matrix is a powerful tool used in the study of second-order behaviors. It will help us to evaluate the maximum, the minimum, and the saddle point. Okay, f(x)(x) stands for the second derivative in x direction, f(y)(y), the second derivative in y, and f of xy, it is the mixed derivative, as you can see. That's the general shape for the extension of the Hessian matrix in the case of dimensions Open dimensions up to n and n if you wanna put it to n and n as you can see. Once more, this part to complete the discussion, I wanted to complete the discussion of this part, although this is not with us in the main slides, but we will go to them down the road. Okay, how the slope change is changing? This is a geometric interpretation of the Hessian matrix and whether the surface is curving up or down. If I want to use the analysis of maximizing or finding the maxima and the minima, all I have to do is to get the value of d, which is simply f double x, f double y, minus f of xy to the power of 2, or getting the determinant of the Hessian matrix. So d is the determinant of the Hessian matrix. Okay? طيب, according to the value of d and the value of f of x double x, I can know if it is a local minimum or maximum, or a saddle point, or if the test is inclusive. So if d is greater than 0 and the f double x is greater than 0, then I have local minimum. If d is greater than 0 and the f double x is greater than 0, I have a local maximum. If d is greater than 0, I will have a saddle point. If d is equal to 0, then the test inclusive. Once more, d is the determinant of the Hessian matrix. If you remember, Omar, that's the shape of the Hessian matrix. fxx, fxy, fy, and x, and the f double y. That's the shape of the Hessian matrix. So if you remark, I'm multiplying the elements of the principal diagonal minus the elements of the secondary diagonal as we use to evaluate the determinant of the two, which is going to give you the value of d as you can see. In order to conclude this part, let's discuss the optimality and the origin of f of xy equal x squared y squared. So if I made f double x, I will differentiate this function 2 times with respect to x. The first is going to be 2x, second derivative is going to be 2. Differentiating with respect to y 2 times, it's going to be 2y, then differentiating more, it's going to be 2. F of xy, I will differentiate the function with respect to x, then with respect to y. With respect to x, it's going to be 2x, with respect to y, it's going to be 0. This is why f of xy is equal to 0. The Hessian matrix is fxx, fxy, fyx, fyy, and that's the shape. Let's evaluate d, which is the determinant of this matrix, which is going to be 2, which means that d is greater than 0, so it's positive 4. And also f of xx equal to 2, which is greater than 0. So from all of this, it's a local minimum. And that's really the shape of this function. If you look to the shape of this function in x, y, and z, it will represent a paraboloid. That's the shape that we are talking about. And at this point, it will be at 0, 0, and 0. So this is y, that's x, and that's z. That's the crown of our function, as you can see. So once more, positive means local minimum, negative local maximum, and the mixed sign at the center point. Summary of all of this: the Hessian, the matrix of second partial derivative, it describes curvature of multivariable function. It is essential for classification of critical points, and it connects the eigenvalue and the quadratic forms, as we will see down the road. And I believe we come to the end of our work today by this slide, and I will continue next lecture, inshallah. That's another problem. As I told you, I usually feel more comfortable by giving you more than one example for e of x and y. Those are the first derivatives. I will get the second derivatives for all of them. Then I will try to build the Hessian matrix. That's going to be the shape of the Hessian matrix of this problem. Remark that you can, in the exam, if it is a it's an MCQ, he will ask you to choose the correct answer. If it is in the part of open question, he will ask you to bring the Hessian matrix as usual. Thank you very much for attending today, and thank you for listening to this lecture. Please don't forget to try to solve as much as possible, and please use your pen in solutions. Try to rewrite everything once more through your solutions. Thank you very much. Appreciate it, and I will see you next time, inshallah. Thank you.
Thank you, Dr.
شكرا.